Hello, in this video I'm going to go through a few kinematics questions so that we can talk through them and go for a more insightful approach rather than the formulaic just crank the handle approach that they push to us in textbooks. So I'll start with this fairly simple question of a cyclist travelling with constant acceleration x meters per second squared in a straight line from rest to 5 meters per second in 20 seconds. Then decelerates back down to rest with constant deceleration of half x meters per second squared. So we need to find x and the total distance travelled. Right, so rather than jumping in, a lot of people will look at this and think, oh yeah, we've got one-dimensional kinematics, we've got constant acceleration, so that means SUVAT. You know, I'll stop pulling out my v equals u plus at and things like that, which, you know, is fine. But let's just say instead, well, the acceleration is the rate of change of the velocity, and because we've got constant acceleration, we can say, well, we've got a change in velocity of 5 meters per second in 20 seconds, so the acceleration, which is x in this case, must be 5 over 20, 0.25 meters per second squared. So that's a much quicker way of doing it. We're just talking through what velocity and acceleration actually mean. Then we need total distance travelled. Right, well, if it's decelerated, if this cyclist has decelerated at half the magnitude of the initial acceleration, then it must take twice as long to get back to rest. So we've got 40 seconds on the deceleration, but you'll notice that we've got the same average velocity on both of them, that we've got 2.5 meters per second is the average magnitude of the velocity. It's our average speed in each part. So if we're looking for total distance travelled, well, speed is what we want. So we're travelling at 2.5 meters per second on average over the entire journey for 60 seconds. So the total distance travelled, d, is going to be 60 multiplied by 2.5. which is 150 meters. You could have broken that into 2 bits. I mean, it would have been the same result, as in we've gone from 0 to 5, so that's an average of 2.5 for 20 seconds. So we travelled 50 meters, and then we would have travelled 100 meters on the way back. But we haven't had to explicitly write out, oh yeah, we've done a v equals u plus at and go through that approach, where you can lose sight of what that actually means. I know we essentially use that in making that calculation, but we use the concept rather than this sort of abstracted formula. Right, so moving on to another one, we've got a particle moving with constant acceleration in a straight line again, so we're in the same kinematics with one dimension. Passes through 3 points A, B and C with velocities 20, 30 and 45 meters per second respectively. Time taken to move from A to B is t1, time taken to move from B to C is t2. Right, so we need to show this. Well, I mean, from a conceptual point of view, this ratio of the times is obvious because we're going up 10 meters per second between A and B, and we're going up 15 meters per second between B and C. So we've got that ratio where we're going from 10 to 15, and we know that that change of 10 is the acceleration multiplied by the time in each case. So that is the acceleration multiplied by t1, and that's the acceleration multiplied by t2. So we're using the same concept exactly as we had in the previous question of the accumulation of the acceleration is the change in the velocity. So that just simplifies down to 2/3 equals t1 over t2, which is exactly what they were looking for. Right, so they now tell us that the total time for the particle to move from A to C is 50 seconds. Well, this ratio here, remember when you were going through your maths that fractions and ratios are the same thing. You know, we can describe these as ratios. I mean, that's what they are. So there's 50 seconds. We're dividing up in the ratio of 2 to 3 between T1 and T2. So for 50 seconds, this means that T1 must equal 20 seconds and T2 must equal 30 seconds. So if we want the distance from A to B, that is going to be the average velocity multiplied by the time. So the distance from A to B, average velocity 25 meters per second, multiplied by the time of 20 seconds, and that is going to give us 500 meters. So yeah, rather generous, as they often are in books, with 8 marks there. But again, we haven't had to pull out a SUVAT equation, which is the main thing I'm trying to highlight in all of these questions. Moving on again, particle moving in a straight line with constant velocity. Yep, same old story. Constant acceleration, sorry, same old story. 5 meters per second squared. Velocity of the particle at A is 3 meters per second in the direction of AB. Velocity of the particle at B is 18 meters per second in the same direction, right? So it's increased by 15 meters per second at 5 meters per second squared. So that must be 3 seconds that is traveled for. So T must be 3 seconds. We want the distance from A to B, so that is the average velocity multiplied by the time. So the distance is 21 over 2, so 10.5 multiplied by 3, which is 31.5 meters. So again, we're in the zone now of these. Particle moving in a straight horizontal line at constant deceleration, 4 meters per second squared. At time t equals 0, particle passes through point O with speed 13 meters per second, traveling towards a point A, where OA is 20 meters. Find the times when the particle passes through A and the value of t when it returns to O. Right, so this one is more involved because we now do have, this is where SUVAT can come in handy, because we'll be more or less creating a SUVAT equation. So there's more information here. So let's write some of this out. So we've got acceleration is -4. We've got that our V0 or our U, depending on how you want to put it, is 13 meters per second. We don't know what V is. So V is when it's going through A, point A. So V at A. We know that the displacement is 20 meters. And we'll see with this that we are going to be pretty much conjuring up our S equals UT plus a half AT squared equation, because we'll be saying that VA is going to be 13, and then we're adding on the accumulation of the acceleration. So we do -4 times t. And then we're going to say that the displacement, 20, is going to be equal to the average velocity multiplied by the time. So that's going to be 13 minus 2t, all multiplied by time. So we've talked through it in that way, in a conceptual fashion. But if we had just jumped in using SUVAT, which is why this one can be useful, and said, well, S equals UT plus a half AT squared, then that is what we've got here. Yeah, we've got 13 is our U, so 13t, and then minus 2t squared. So that is our plus a half AT squared. So with talking through conceptually in kinematics, although it works fine, you find that when you get the ones where you don't know something in the middle, usually with one of your velocities is missing, then you end up constructing a SUVAT equation. So this goes to show that concepts are great and you can still use this approach, but you want to be able to draw on a SUVAT in certain cases because it will make things a bit quicker for you. Right, so now we need to solve this equation. So we've got, what have we got? 2t squared minus 13t plus 20 equals 0. So yeah, we want to try and solve for this. So we need two numbers that multiply to give 40 and add together to give minus 13. So we're going to need a -8 and a -5. So split the middle term, 2t squared minus 8t minus 5t plus 20 equals 0. We've got 2t times 2 minus t minus 4, and then minus, well, let's put plus. If you want plus, no, let's do minus 5 times t minus 4, because we want to keep the t minus 4 the same. So 2t minus 5 t minus 4 equals 0. So that gives us our 2 times of t equals 5 over 2, or t equals 4. So that's our 2 times when we're passing through A. Now the second part of this is probably going to be easier because we're not concerned, we haven't got a missing v, and it's that one in the middle that's a pain. So the value of t when the particle returns to O, well, that's twice is the, going out to the resting point. If you think what's happening, it's going out and then it's turning around and coming back. So if it started at 13 meters per second and it's decelerating at 4 meters per second, it's going to take 3¼ seconds to hit 0. So we've got 3¼ out, and then we'll have 3¼ back. So it's going to be 6½ seconds in order to return back to O. So that one's a lot easier because we knew our starting and end times. As I say, it's usually the velocity ones that draw us into using SUVAT straight off. So yeah, important part of this question, don't completely disregard SUVAT. You can get away with not using it, but jumping in straight onto S equals ut plus half at squared just saved us a little bit of time going through these steps. Right, this one I've actually put up. This is something out of a maths textbook, and I've put the suggested solution that they had in the textbook just here on the side. We don't need to go through all of the detail of this. I just wanted to highlight how much working out there is in these two parts of this question that we're going to look at, including this diagram. So there's quite a lot they've done in the textbook. So let's see if it is actually as complicated as this. We've got a particle P moving on the x-axis with constant deceleration of 2.5 meters per second squared. At time t equals 0, the particle passes through the origin O, moving in the positive direction, speed 15 meters per second. Right, find the time between the instant when P first passes through O and the instant when it returns to O. Right, so this is like what we had in the last question. So we're going at 15 meters per second and we're reducing at 2.5 meters per second every second. So that's going to take 6 seconds to hit 0, and then it's going to be the same on the way back. So straight off, we know that's 12 seconds. Now they've done all of this working out here using SUVAT in order to get 12 seconds for something that you can just state pretty much. Right, total distance travelled by P during this time. Well, we know it's 6 seconds on the way out, and that's got an average velocity of 7.5. So we need to do 7.5 times 6. 7.5 times 6, and we got the same on the way back. So we multiply that by 2, and that'll be our total distance travelled. So that's 6 times 15, which is 90 meters. And they've done all of this for it. So whereas the last question really showed the value of, you can save, I don't know, 30 seconds or so by applying that S equals ut plus a half at squared, this one is showing the value of not just blindly going through SUVAT. They've done SUVAT. I mean, it's just so tedious of doing all of that to get things that are so obvious. So don't get caught in that trap.